Today we'll be taking a look at problem 1.7 from Griffiths Introduction to Quantum Mechanics 3rd edition. In this one we're asked to calculate the derivative with respect to time of the expectation value of momentum. We're going to do this using Ehrenfest's theorem, which, as it says there, asserts that expectation values obey the laws of classical mechanics. Alright, so getting into this problem, we're just going to have to start with a Schrodinger equation. We're essentially starting from scratch, and we're just going to solve all the way through until we get something that looks like this, using whatever substitutions we can, whatever methods we see. And this is a super math heavy problem, so feel free to watch it on 2 times speed to get through it all the first time perhaps, and then if you have to go back and watch step by step, maybe you can do that. But it will be a long problem to solve just due to all the math. Alright, so starting off we have Schrodinger's equation. We're going to write it out. IH bar d psi dt is equal to negative h bar squared over 2m d squared psi dx squared plus the potential. We'll just do v, that's v of x, and then psi. Alright. Now we're going to divide both sides by IH bar, and we're going to write d psi dt is equal to negative h bar over 2m, 2mi, d squared psi dx squared, plus, but this is actually going to become a minus, I over h bar. It would be plus 1 over IH bar, but we're just going to throw the I in the numerator, and that's going to turn it into a minus sign. And then we have our potential, and then psi. And continuing on here, now we can write what we'll need here. We're going to need d psi dt, and we're also going to write d psi star dt. These are 2 very important equations that we're going to use throughout this problem here, or I should say substitutions that we're going to use. So we're going to have IH bar over 2m, d squared psi dx squared minus I over h bar v psi. Okay, and we're going to take that exact thing, copy paste it right here, except we're going to flip the signs, of course, since we're dealing with the complex conjugate. Alright, and I'm going to call this one equation 1, and I'm going to call that one equation 2 for substitution purposes later. Alright, and we also know that psi is equal to psi of x comma t, and v is equal to v of x comma t. Okay, so that's really our potential. Technically, if you want to be specific about the proof here, we can write that out. Alright, now by Ehrenfest's theorem, we can write kind of the assumption upon which this whole problem is based, and that's that the expectation value of momentum is going to equal m times the expectation velocity, because of course p equals mv, momentum equals mass times velocity, and then we're going to say that, well, that equals m times d x dt, x being expectation value of x. So we're just plugging in, again, these are just our classical laws, as it says there in the problem. We're going to say that the expectation values are going to obey the classical laws. So that's all the problem says. Alright, so now we have to start by finding x. So find, expectation value of x. So find expectation value of x. Well, how are we going to do that? Well, we have an obvious formula that we learned from any quantum physics textbook. We're going to do integral from negative infinity to infinity x times the wave function squared dx. Okay, we're going to plug this in, therefore x is equal to negative infinity to infinity x, and then we're going to, well, actually what we're going to write here is psi of x t times x times psi star of xt. So that's by definition dx. So that's by definition. of the wave function squared, and we're just going to throw the x in the middle there. And then we're going to differentiate. So differentiate with respect to t. All right, because we're trying to find d dt of expectation value of x. So that's what we're getting now. All right, well, that's going to be d dt of exactly what we just wrote up here. So for the sake of speeding things up, I'm going to copy paste that. Okay, so we need to find the time derivative of that thing, and that's going to be our derivative with respect to time of expectation value of x. All right, well, what we can write instead is that is going to be equal to the integral from negative infinity to infinity of x, and then the only things with t in them are those wave functions. So we're going to take the d dt inside, and we are going to do d dt of psi of xt psi star of xt, and then dx. Okay, once again, we brought it inside because nothing in the integral itself is, with respect to t. The only thing with respect to t are those two wave functions. So we're going to bring the d dt inside and do that derivative in there. And then what that leads us to is just a simple application of the chain rule. So we're going to have the integral from negative infinity to infinity of x times d psi star dt times psi plus psi star d psi dt. And then we're going to have all of that integral over dx. All right, now sub in equations 1 and 2 from up here that we already wrote. We're going to sub those in now and see where that gets us. And this is where it starts to get kind of messy, but also, quite frankly, if you're a physicist, it's amazing. This is really neat math. So dx dt is equal to integral from negative infinity to infinity of x, and then we're going to open a big bracket here and start plugging in. So we're going to have negative I h bar over 2m d squared psi star dx squared. Make that partial there. And then we have plus I over h bar potential psi star multiplied by psi. Okay, and then we're going to have plus psi star multiplied by I h bar over 2m d squared psi dx squared minus I over h bar potential, and then the wave function. All right, close the big brackets, dx. So obviously that's a really big integral, and we're going to see what we can get to cancel out. Well, if you notice, when we actually end up multiplying these, the psi and then the psi star in, when we actually do that, what you're going to notice is that this term here, IH bar V psi star psi, is going to cancel out with minus I over H bar V psi star. Those are going to cancel out. Okay, just opposite signs, it's the same term. All right, what we're going to be left with then, we're going to say dx dt is equal to integral from negative infinity to infinity of, let's see, we have x out front still, and then in our parentheses we have negative IH bar over 2m d squared psi d squared psi star dx squared multiplied by psi plus I h bar over 2m, and then that is psi star d squared psi dx squared. So obviously those two don't cancel because the conjugate is in the second derivative here, and just the normal wave function is in the second derivative there, so we can't cancel those. But we can go ahead and simplify this further by bringing out the constant terms. So that is going to be equal to I h bar over 2m times that integral, negative infinity to infinity, of x, and then we're going to take out a d dx as well, and we're going to be left with negative d psi star dx times psi plus psi star d psi dx. And dx. So hopefully that was clear. We just took out our constants, I h bar over 2m, and we also took out one of the second derivatives there. Or we took out that second derivative and put it in front. All right. So from this point, we can do our beloved integration by parts. And just a quick reminder here, integration by parts, integral of u dv is equal to uv evaluated at the bounds minus integral v du. All right, so in this case, we're going to have, continuing on here, get a new page, that equals I h bar over 2m, big bracket, we'll do x negative d psi star, that's terrible, d psi star dx times psi plus psi star d psi dx evaluated from negative infinity to infinity minus integral from negative infinity to infinity negative d psi star dx times psi plus psi star d psi dx, and then we'll have dx there, and we'll close the bracket. So clearly this is getting a little bit like I said, it's a little math heavy, but what we can notice actually is that this right here, if we evaluate at these limits from negative infinity to infinity, you'll actually notice that this is going to go away. This is because of that x, that's going to be odd over symmetric bounds, so that's going to go away. That's going to be that's going to allow us to zero that out, and we're really just working on the bottom now. Okay, so that equals I h bar over 2m times integral negative infinity to infinity, and we're going to say d psi star dx times psi minus psi star d psi dx dx. So that's what we're left with right now. And just to a reminder, we're just solving for the time derivative of the expectation value of x right now. That's all we're doing. Now, as we go on, we're going to do integration by parts again on that first integral here, and then we're going to still be subtracting the second integral right here after the minus sign, and we're going to see that we're left with I h bar over 2m, and then do your integration by parts. We have psi star evaluated negative infinity to infinity minus the integral from negative infinity to infinity of psi star d psi dx, and then we're actually going to subtract that one more time. And so that was from our integration by parts, and now we're going to pull this down again. You'll see that's actually the same term. So minus the integral from negative infinity to infinity, psi star d psi dx dx. Okay. And that's all being multiplied by that IH bar over 2m. So we're going to close our parentheses, and we're going to note that that's 0 by definition of the wave function. And we're going to say, okay, well, this is equal to IH bar over 2m times negative 2. We have negative 1 of that term minus another one of that term, so negative 2. Integral negative infinity to infinity of psi star d psi dx dx. Well, our 2's cancel out. We're left with that negative 1 still, though. And we see that ddt of the expectation value of x is equal to negative IH bar over m times the integral of from negative infinity to infinity of psi star d psi dx dx. All right. Now let's go back up to Ehrenfest's theorem, which we wrote down our primary statement right here for the problem. This is really what we're focusing on. So now we have dx dt. Well, now we just got to multiply that by m. Okay, so, and that is going to equal the expectation value of momentum, which is what we're trying to figure some things out with with the time derivative of the expectation value of momentum. That's what we're really trying to get to. So let's multiply by m so that we can get that. So now we have, obviously the m will go away, that's in the denominator right there, so we can say m dx dt is equal to negative IH bar integral from negative infinity to infinity psi star d psi dx dx. Okay, and that, of course, is equal to p, or expectation value momentum, I should say. Okay, now let's try and rearrange some things and see what it looks like. So if we take that negative IH bar inside of the integral and we kind of disconnect that ddx for a moment from that, from psi, let's write it like that. We'll see that p, or expectation value momentum, is equal to the integral from negative infinity to infinity of psi star, and then pull in our negative IH bar, because that's just a constant term. We're going to grab our ddx, and then we're going to have our psi. So that ddx is still being applied to psi. We can't change that, but just the way that we're writing it is a little bit different. And what's really interesting now is, well, we can take the time derivative. Well, I should stop for a second and note that this is a very suggestive way of writing this, because we know that the momentum operator is, in fact, negative IH bar times the derivative with the partial derivative with respect to x. So by definition, we have just figured out the momentum operator. But that's not what the problem is asking us for. It's asking us for the derivative with respect to time of the momentum operator. So in order to do that, we're going to rearrange things again. We're going to do ddt of that above. So I'll grab that real quick. So derivative with respect to time of that, which we already wrote. And essentially, if we can, we'll write it like this. That is equal to negative IH bar, integral negative infinity to infinity, and then we're going to say ddt of psi star d psi dx dx. Okay, now this is just another case of the chain rule. So we'll write is that is equal to negative IH bar, integral negative infinity to infinity. We're going to have d psi star dt times d psi dx. And we're going to open a big bracket here as well. Plus psi star, keeping our chain rule here, we're going to do psi star, and then we're going to do ddt of d psi dx. We're going to close the bracket, we have dx, and now prove that the time derivative of the expectation value of momentum is equal to this expectation value of negative dv dx. So that's our final step in this problem. And how are we going to prove that? Well, again, this is going to be some nasty math, but we're just going to go through it. And I say nasty, but really, like I said earlier, it is really neat how it works out. And it's neat to see how the physics works here. So let's go ahead and prove this. So we have that, well, we'll start with this statement here that I wrote above. And we're going to plug in equations 1 and 2 from the very beginning. And I'm going to go up and grab those real quick to make it easy to reference those. Going back down here. Okay, so we're going to plug those in anywhere that we see d psi star dt or d psi d or d psi dt. Okay, so if we do that, that is equal to negative IH bar integral negative infinity to infinity, and then we start a big bracket. I'll do a little parentheses, negative IH bar over 2m, plugging in, d squared psi star dx squared plus I over h bar, potential, our wave function, but this is conjugate, and then we have d psi dx multiplied there, and then we have plus psi star d dx of IH bar over 2m and d squared psi dx squared minus I over h bar v psi, close that, dx. Okay, now this is where it gets a little tricky because you could easily miss this part. This d dx, that is going to be a chain rule because your potential and your wave function are both functions of x. So don't miss that part. That's probably one of the easiest parts in this problem to miss as you're just going through because it gets really crowded here. Don't miss that chain rule there. So what we're left with then, actually we're going to expand this out quite a bit. We're going to have negative IH bar in the front, our integral, negative infinity to infinity, and then we're going to have a big bracket here, negative IH bar over 2m, and then d squared psi star dx squared d psi dx plus I over h bar v psi star d psi dx. Okay, and then we have plus psi star and then IH bar over 2m d cubed psi dx cubed, and then we have minus I over h bar v psi star d psi dx Make that a little cleaner. d psi dx. And then we have minus I over h bar. Again, this is the chain rule here. dv dx psi star psi, close that big bracket, dx. So that's the fully expanded notation there. Well, it's clear that this part is going to cancel with this part, negative and positive. And then we can write this as equal to negative I h bar. And then we're going to do a big bracket here, and we're actually going to pull out our negative I h bar over 2m, since that is in the first term there. We're going to do integral negative infinity to infinity d squared psi star dx squared times d psi dx dx. Okay, and then we're going to go to our next integral plus I h bar over 2m. That's that constant there. So plus I h bar over 2m integral negative infinity to infinity of psi star d cubed psi dx cubed dx minus I over h bar, that's our final constant term, integral negative infinity to infinity dv dx psi star psi dx. Close the big bracket. Okay, so we're getting closer. We just have a few more steps. This is going to be, we're going to have to use integration by parts again for this evaluation for the first term here, for the first integral here. So integration by parts, plugging everything in, we get that is equal to negative I h bar, and then open our big bracket again, another negative I h bar, this time over 2m, and then we're going to have d psi dx, d psi star dx. We like that because that is evaluated negative infinity to infinity. By definition of the wave function, that's going to be equal to 0. Then we have plus I h bar over 2m, and then negative infinity to infinity. And we have d psi star dx, d squared psi dx squared dx. Okay, so that's the second part of our integration by parts. And then the rest of this is actually just going to follow. We have this plus this term minus this term. So I'll just carry those down below. Copy that, paste it. Okay, so plus that, minus that. Good. And as we keep going here, we can see that we have another integration by parts due to, if I'm correct here, let me make sure I'm writing this correctly. Yeah, well, I'll just write it out. So that is equal to negative I h bar, and then we have our big bracket I h bar over 2m, and we have integral negative infinity to infinity d psi star dx, and we have d squared psi dx squared dx. Alright, and then we have plus, and we're actually going to bring a lot of things under the same integrand here. So negative infinity to infinity, and we're going to do I h bar over 2m of psi star d cubed psi dx cubed minus I over h bar dv dx psi star psi dx. Okay. So as we do integration by parts, This is going to be like our dv part, that's going to be like our u part right there. So as we do that integration by parts, we see that that is equal to negative I h bar, and then we're going to do I h bar over 2m, and then we're going to have psi star d squared psi dx squared evaluated negative infinity to infinity, and you can see that that's just going to be 0. Okay, and that is minus I h bar over 2m integral negative infinity to infinity psi star d cubed psi dx cubed. All right, dx, and then we're going to have actually a plus from this plus right here. We're going to have plus I h bar over 2m integral negative infinity to infinity psi star d cubed psi dx cubed dx. So because of that, we're going to cancel these two out. So cancel out. Cancels. All right. So we've taken care of that, and then we just have minus I over h bar integral negative infinity to infinity dv dx psi star psi dx. Okay. So this is when we can start kind of compiling everything together. We see that this is equal to negative I h bar times negative I over h bar, and then we have negative infinity to infinity psi star dv dx, and then we have psi dx. Okay, well, our h's cancel, our i's square, and then obviously I squared is equal to negative 1, so we have negative 1 times the integral from negative infinity to infinity psi star dv dx psi dx. Okay, so what did we prove? Well, if we want to write it like this, we can say the time derivative of the expectation value of momentum is equal to the integral from negative infinity to infinity of psi star, and then in the middle we have this negative dv dx term, and then psi dx. Well, by definition, we know that that is equal to the expectation value of negative dv dx. And so we proved that the time derivative of the expectation value of momentum is equal to the expectation value of negative dv dx.